This afternoon, we're going to hear about the SOCIONICAL project from Professor Dr. Paul Lukowicz. I'll tell you very briefly something about Paul, and then we'll break for tea and come back for the panel discussion. Paul is at the Embedded Systems Laboratory at the University of Passau in Germany. One thing I think that's very impressive is that he actually has two MScs, one in computer science and the other one in physics. So he really brings two different worlds together. His particular research is the application of mobile devices and on-body sensors in various applications ranging from, can't read my writing.
Emergency healthcare.
Thank you. And consumer.
Sports, consumer, okay.
Now, the other thing I'd like to tell you about Paul is that he is an amazing coordinator, because he's the one who actually got 14 partners together to create this project funded by the European Commission, and it is his skill in how to write a brilliant proposal that got us 7.2 million. So well done, Paul, and please carry on.
So as you've said, after those talks that gave a very nice practical insight into sort of the world of emergency, I'm going to give you an outlook into the future, as a research project is supposed to. And it's still very nicely built on some of the things that were said. And looking from this picture, we said people using a megaphone to address a public being engaged in accidents, to going toward modern technologies like Twitter, mobile phones, Facebooks, which has already been mentioned, and actually looking beyond, what are the technologies that could emerge? And one thing that's very clear, we're not a project that develops technology and tries to deploy it. We're rather a project that looks at technology and try to understand what sort of impact would certain technologies that are just around the horizon have on large-scale disasters and other situations. So first I'll just tell you a few words about the project itself. Then I'll talk about technology, mobile phone technology from a different angle of what it can do today and what could be very useful tomorrow. Talk something about complexity science and models, and conclusions, what we think the project can provide to people like you, political decision makers, to people from industry, in terms of information of service. So starting with the project, the interesting thing about the project, apart from being large, having a lot of money from the EU and a lot of countries, is that it's a project that brings together people like Eve, who work in the political, social area looking at complex systems, brings together companies, people from theoretical physics, people from computer science, so very, very different angles that look at this problem of using technology in large-scale disaster and traffic scenarios. And if you look what the project does, that's our project statement: complexity science-based models of socio-technical systems with ambient intelligence. A lot of buzzwords. That had you guessed 7 million from the EU. You have to use the right buzzwords. But I will not be explaining the buzzwords to you. I'll just give you an example. And also a disclaimer for the example, it's not a proposal how to do real-life deployment in an emergency. It's rather a concept of a vision of what the technology could possibly give you. So imagine something we already had mentioned. So we have some sort of a large structure, building, subway, stadium, whatever, where you have an emergency and you have people who try to evacuate. What you have already heard from other speakers is that information is an issue. Infrastructure might break down, no mobile phone communication. And people are disinformed. So the issue, how do you develop some sort of a situational awareness, and how do you disseminate this situational awareness to the people, and how do you make them take some useful action based on that information? It's certainly an issue. And now imagine that you use technology in the following way. Now imagine that a number of people involved in this disaster had some sort of sensor devices that could sense, for example, temperature and visibility. And actually, you do have devices that can sense visibility, which are mobile phones with a camera. So it's not that far-fetched. Now imagine you had the devices that could sense things like crowd density, people movements, type of movements. And actually, we had devices that could sense their very existence, which means a dropping of a device from being online means that something catastrophic happened. And now imagine that you had devices that could propagate that information throughout the crowd. And when I talk about propagating, I explicitly mean peer-to-peer communication, which means no need for any phone network, no need for any infrastructure. What happens, and that is something that is done today, the way teenager distributes some illegal videos or music is essentially from phone to phone via Bluetooth. And Bluetooth is short range, but every phone has a Wi-Fi connection which takes something like 50 meters. So this whole idea of distributing information in a situation with no infrastructure except people having mobile phones is, as one of people said before, not a technology problem. It's just a problem of somebody saying that mobile phones have to have an emergency mode that allows that. And that is a small piece of software that would be activated, and you could actually do that. So if you imagine that you have something like this, you could now, without any intervention from above, so to say, create a significant level of situation awareness and distribute that information throughout the people involved in the incident. And you can have different channels of distribution. And in the end, of course, the vision is that you could have some sort of a software on the devices that would use this information to somehow direct those involved or some sort of a useful evacuation. And what we are talking here about is something that would involve, again, on the local interactions. So, of course, if one of the phones found a way to communicate to the outside world, you may provide this information to some sort of a emergency center who would provide instructions. But otherwise, the question is, can we use the technology to help people self-organize? That's one of the statements we already have. People are very proficient at somehow saving their own skins. That's millions of years of evolution. The other ones got eaten by the tigers. And the question is, how can this technology actually help people? And very clearly, it's not a trivial question, because if you just distribute the information about where the fire is or where the non-congested exits are, you may create what you know from this traffic routing systems, everybody going for the same exit and just moving people between the exit. The information that you derive might not be spread properly, it might be too late, and you may create a lot of funny effect. You may have at the end people running between one exit and the other. So the technology is in a way there, but understanding what this technology does, kind of bottlenecks a lot of stuff on a global scale, is something that is really interesting and certainly unknown. And that's what I would like to emphasize. What we are trying to do in the project is not to build the technology and throw it at humanity. What we are trying to do is to understand what the technology could do and develop simulation tools and models to first develop an understanding of what sort of impact we would actually have. And we have in the project people like Eve who are talking to people like you to understand what are these sort of political consequences, where this thing could be useful, and to do this sort of a projection. So the questions that we are trying to answer in the project is, first of all, what is it that technology can give us? And I would like to emphasize, again, like one of the previous speakers said there, a lot of this technology is something that as a hardware and software, it's there. I'll show you that. The second question is, and that's also what we are trying to understand with social sciences, how would the people react to this sort of technology? And I think the reaction can be very different. So those of you who will, go and, who are sort of the older generation, would probably rather follow another human than what your phone says. I bet you that 14, 15 years old would first look at a phone and then look around. So the question of trust, of reaction is very important. And then, of course, once you have those two parameters, what technology can do, how will people react, you can try to develop models. And that's where complexity science come in, is what will this actually do in a global scale? So assuming you distribute, and again, we have had this discussed in the morning, you do not always want to distribute every information to everyone. So assuming, can we find modes where this information that our devices can derive can be distributed in such a way that it will have a positive effect, sort of enforcing people's tendency to save their skins rather than creating havoc and possibly assisting anybody who might come from the outside. So that's sort of the broad goals. Let me now look at the technology, which some of you know, some may not know. And of course, at the core of the technology is my favorite toy, the iPhone. And as you know, the iPhone, as many telephones, has a GPS sensor, not very useful in the subway, but it does have a compass and acceleration sensor. Essentially, it measures motion. Some of you may not know it has a humidity sensor. so that if you actually put your iPhone into the water, you will not get your guarantee refunded. But it does have that sensor. Has an infrared proximity sensor. It has a camera and a microphone, very useful sensors for finding things out. It has Bluetooth and Wi-Fi connection, which are both communication means, and again, means of communication, totally independent of any telecommunication provider or any infrastructure. And also sensors, because if I don't know, if you switch on your Bluetooth in a train or your Wi-Fi, you see a lot of other people with Wi-Fi there. So actually you know who is around you. So what can you do with a mobile phone? Well, the very simple thing you can do, you take your acceleration sensor, you can see somebody is walking, how fast he is walking. You can see even more. You can see if somebody is walking up or down, if he's limping because there's a problem with his leg, if he's running, if he's nervous. All those things you can get from a simple acceleration sensor on a phone. And it's not theory. That's something I let my bachelor students do as an exercise. So that's really easy. What you can also do with a phone, you can do location. So one way of doing location is using wireless LAN if some access point happen to be working. The other possibility is if you use the compass and the acceleration sensor, actually to a degree you can track people where they are going. So you could develop an understanding of who is where within the subway just by looking at the signals from the phone and having them communicate. Another absolutely brilliant sensor is sound. I mean, close your eyes, listen, you know where you are, you know what's happening. You know when there's an explosion, you know when people are screaming, everything. And of course, your mobile phone has a sound sensor. Every phone has a microphone. You can actually switch it on, and you can put it in a pocket. It will still recognize a lot of things. So I've done experiments, very, very easy, again, bachelor level work to recognize these things with a phone. And recognize devices, a lot of stuff. Another sensor, as I said, Wi-Fi, Bluetooth allows you to detect proximity. So if you look at people in a crowd, and you are now running an experiment on that, and you have them switch your Bluetooth stuff, you can sort of have an idea of the topology of those people without having any GPS signal, and you can understand how the crowd moves. You can understand where it moves, you can understand something about crowd density. And if people actually manage to make calls, yes, you can do voice recording, but you could have software that analyzes stress. And this way you can actually see people who are maybe close to panic, and an experienced operator recognizes it automatically, but that is something that could help. So in summary, what you see is a small phone, but it's a very big brother. And I think a lot of people don't understand how much information you can extract from a mobile phone. And in terms of extracting this information, like people's motion, location, situation around them, things like panic, again, fire, you can really do it today with simple tools. And of course, it doesn't work with 99.9% accuracy. But if you're looking at thousands of people in the subway, and say every 10th of them would have a mobile phone with that capability, even if you have 50% accuracy, just by pure statistics, you are going to get a reasonable picture of what is happening there. And again, those devices communicate. They can actually spread information that is injected into the crowd. They can communicate themselves. They can help people self-organize. So there's a huge potential. And as had been already mentioned, there are a lot of such devices. People have watches. I had a watch with a air pressure sensor, and that actually lets you tell how high you are, and lets you tell how you change, go from one floor to the other. I had a watch with a temperature sensor. Those things are Bluetooth connected, so you already have this sensing infrastructure. And of course, the problem is that all of this, or the nice thing is that all of this stuff is now globally connected. So we had this discussion about Bluetooth and Twitter being communication channels, but which people can by themselves disseminate information. And now you're going a step further, because typically if you're running from a fire in the subway, you will not be tweeting about that. Maybe 10 years from now, that's what teenagers will be doing. And we know the stories of people doing tsunami. We have one guy who worked with a tsunami catastrophe in Asia. And you have this scenes of people, filming this wave. Wow, is that a cool wave? So this thing does happen. But in general, that's not what people do. However, if you have now those phones automatically monitoring what's happening by sensors, you could actually have the sensor information being tweeted to the outside world. And actually even being translated. So you could have this automatic dissemination of information through social networks. This combination of the social network concept with this situational awareness is something very, very powerful. And to a degree, people are using it. You now have this tool with Google Maps where you can register with friends, and friends can see where you are on the map. That's what we had this example of teenagers organizing their Saturday night activities, and that's exactly what's happening already. So we are talking about just taking this concept and putting them to a more useful thing than allowing a bunch of young people to get drunk quickly. So that is something that is really a powerful concept. As I said, in SOCIONICAL, we are not as much developing this technology. That's something that, for example, I do in my lab in different projects. We are trying to look and understand what would the impact of such technology be on actual disaster scenarios. I think I can repeat what has been said before. In a way, it's not about the technology not existing. It's about this, having a support from policymakers to deploy this technology, and actually somebody doing some implementation. But it's not a fundamental issue that you wouldn't have the technology to do these sort of things. So next we come to the models. So essentially what we do in SOCIONICAL is that we look at two types of scenarios. The first one is this emergency scenario, so any sort of a large-scale incident where we would like to use this type of technology to create situational awareness and to create it in a local distributed way. So it's not that firemen go there, it's just by the virtue of people being there and having devices, and those devices being able to communicate with each other without any external infrastructure, you create a level of awareness. And that's something that you as a human being know very well. If you're in a city and say you're part of the city becomes sort of more run down, something happens. You talk to a friend talks to a friend, and after some time, just through gossip, everybody knows what's happening and everybody knows that everybody knows it. So that's a very natural way of distributing information, and that's exactly the type of distribution that we would be looking at. Replicated on a way of devices, and what we are trying to understand here is to see what would be the influence from the global perspective. So essentially, would something like that help people evacuate quicker, or would it actually create havoc? Is it something that could be used to speed up traffic, or is it something that would hinder traffic? And just to give an example, again, talk about traffic is the next talk that was supposed to be given by Professor Fersha, who got stuck on a plane. So I will show you some of his slides. And this talk is about emergency. And let me just start with a very simple example. We have had this discussion of people, say, during the 7/7 emergency, not having information because the mobile phone network broke down. Now, we could imagine is that somewhere in the entrance to the subway, you would position a transmitter, a very, very powerful Wi-Fi transmitter, that would just switch on the phones inside the subway to some sort of an emergency mode. And deliver a piece of information. And then this piece of information could be just spread from phone to phone instead of the information being spread from mouth to mouth. And of course, the big difference or the advantage of spreading the information via Wi-Fi from phone to phone is that people don't have to meet, but you have some sort of a larger circle of information spreading. Now the question is very obvious. How many phones that are enabled with this sort of technology do you need? What sort of radio range do you need? And how many people do you need so that this information spreads? The whole thing is not very different from classical sort of epidemiological problem. How fast does the disease spread in a population? And we did a simulation, and I don't want to bore you with any formulas, but it shows something extremely interesting. And it underlines that those effects are not very easy to understand. So the question is, how does this speed with which the information spread depend on the radio, on the range of your communication device? And of course, the intuitive answer is the higher the range, the quicker the spread. And it turns out it's not so. So what you see is that in the beginning, by increasing the range, you get something like a linear increase. So the bigger the range, the faster it spreads. And then you get a saturation point in the second regime where you increase the range and nearly nothing happens. So you're wasting energy to go further range without getting any benefit. And then you have a further regime where actually you have an exponential speed off. So what is happening? And that's the type of reasoning that the project is trying to do. So here in this linear regime, the range is so small that if nobody moved, you wouldn't have any information spread. So the information spreads by people moving, coming into radio range, and then progressing the information further. And that, of course, if you include the range, somebody gets the information from another person, he walks, and then another person gets it. Now, what happens if you increase the range of your device is that you are going to get this sort of balls of people who are infected with information. Because you just move a very small bit and you infect the next person. This person moves, infects the next person with information. So what happens is that in the end you have this ball, and this ball grows at its own pace, and the question how large here the circle of your information range doesn't interest anyone. And then eventually, when you increase your range further, you don't have to move the information to spreads like this. So just to give you the idea of why this sort of models are important. It is only by understanding those underlying mechanisms and sort of the complexity theory behind it that you can understand what impact these devices will have on the entire system. So obviously it's a very important information. How can, how fast will the information spread? Will it spread at all? Another example that I would like to show you has to do with location. And coming from Germany, Bavaria, you can look at something like a beer zelt. You would have at Oktoberfest. And now you imagine that you would like to track people. That could be in a large space, and you take a mobile phone and you would like to know where people go. If we talk about this emergency scenario, then what we are doing, we're using the phones to collect information about the state of the environment, about congested exits, about fires, explosions, and distributing it. That is only going to be useful if we can say where this happened. And this is only going to be useful if we can say where a person was, where this information was recorded. If you are talking about guiding people to non-congested exits, you need to know where people actually are to be able to guide them in a reasonable direction. And again, we are talking about some sort of a disaster situation where you may not have mobile phone service, when you are in the subway, so you don't have a GPS. So the only way of actually trying to find your way around is using the mobile phone, the acceleration sensor, and the compass. That's something that can be done. Well, it's not a bachelor, it's a master project, so to say. The problem is it tends to be very inexact. And you can see a number of paths. So you can see here, that is the path that the system says that a person walked. And the thin one is the one that he actually walked. And the more complex paths people walk, the more confused the system gets. So at this in this example, after a couple of meters, the system thinks you're at the wrong exit or something like this, so it's totally useless. So what can you do? And of course the answer is, in such a situation, you don't have only one person, you have a lot of people. And it's sort of this government by collective stupidity, or what you can imagine is that if you have sufficient such systems, they can actually talk to each other and correct each other. I may be off, you may be off, we know we're next to each other, we can correct our estimation. And that is and that would be typical in this sort of a scenario. You would have hundreds of people, each of them would have a device that would be very bad in estimating location, but they could communicate and help each other. And so we did a simulation of that. And so what happens here, we have one guy and one girl walking, they meet, and sort of then the path is collected. What you see here is something like a self-estimate of a device in terms of how accurate the path is. So you have another device, and you see at every place, so this trace is corrected. And what happens eventually, if you look at the outcome, if you had sufficient number of meetings with another devices, then your system provides you an accurate estimation of your location. So what you can see here, the thin line is the line that the person actually walked. The thick red line is the estimation of the system. And the blue line is the estimation of the system without communication with other devices. So essentially what it says, if you were not able to get help from others, you would be totally lost. If you talk to enough other devices, which are as bad as you are, you can actually get a reasonable fix on your position. Now the question from a practical point of view, of course, is how many people do you have to meet and talk to get this result? Is it like, you have to have a tent absolutely full of people? What is the accuracy? Again, this is the type of numbers that we would like to provide to people to say, if you can assume that you have a certain density of crowd and you have a certain quality of your devices, then you can actually locate everyone. And here you see one of those effects, typical sort of complexity science. What you can see here, this is the distance that the person walked. And you can see on the other axis how big is the error that the system makes. And of course what happens is the longer a person walks, the more the system thinks you're wrong. And so the blue curve, the thick blue one, is the curve for someone, a single person. Now we have curves for different number of people here. And you can see that until the number of people raises above a certain critical threshold, the cooperation doesn't help you at all. And then what happens is, above a certain threshold, you suddenly get a transition from a state where all of your systems are lost. So essentially, the longer you walk, the more your system, lets you walk into the fire. But if you have a critical number of people, then the whole thing changes. Then suddenly the arrow stabilizes at something like 2 meters. So that's a typical sort of a phase transition that you have between two different states of a system. Depending on the parameters, you either have a system where everybody is lost, or you have a system where everybody knows where they are. And those are precisely the type of effects that we are looking for. That, if you look at technology, do you have this transition, depending on how you treat your system, between a system where, I don't know, everybody gets killed, and a system between everybody is safe, or majority of people. And of course, those are all theoretical computations, but those are the type of models that we hope to be able to provide, to guide people to understand how technology could actually change the situation for real. So that has been a very simple example that related to sort of sensing and information spread. The project is much more complex, and the way we are trying to proceed is to consider 4 things. First of all, people like Eve actually talk to people like you and try to understand what are the boundary conditions in real emergency situations. So what are the technological conditions, what had actually happened, what are the reactions of people, all the stuff that makes up the practical side. And from those boundary conditions, we try to investigate, what would be useful technology. But then we have people who look more at the psychology, try to understand how would that technology impact people's decision making. So we're looking at making a joint workshop with people from emergency services, with people who actually were survivors of some sort of accidents, to show them different types of technology and understand how they would react. And so this is the next part. How will the technology influence things like development of groups and leaderships? It's a well-known phenomenon in all those type of situations that some people emerge as leaders. Now what happens if you have somebody who is a natural leader, but you have another person who has the iPhone and actually the better information? So how does that influence the entire situation? And finally, what we are looking at is classical crowd dynamics simulations, is giving a certain change in the decision process and given a certain distribution of information, how would that change the crowd dynamics, the evacuation dynamics? So that far for the models and conclusions. What does the project try to do? As you have seen, the structure of the project really is to understand technology, to understand the human and social factors, to understand real life scenarios, and from there to be able to make predictions about how would the system behave, and to do it iteratively, improving the system architectures. And what we are trying also to produce, and that's the job of me here also, is to translate our findings into policy and a recommendation that we could make. And those recommendations go in the direction, what would be developments of the future? What would be things that possibly could be regulated to enable this sort of solutions to make an impact? And that really brings me to the key messages. So technology is out there, and it has been said before, that can actually do amazing things. And in many ways, it's not an issue about developing this technology further, but it's an issue about deploying it and sort of providing an ecosystem, a climate in which this technology can actually be used. What is also important is this ability of today's mobile devices not only to sense but to communicate. So we've heard a lot about communications, but in disaster situations when you don't have infrastructure, this sort of spontaneous peer-to-peer communication between mobile phones can be a crucial technology. And we've done studies, for example, with the Paris Fire Department on the use of this sort of peer-to-peer technology for communication between first responders as well. Another part of the message is that it's really important not just to understand the technology, but to develop a well-funded understanding of what this technology would probably, what sort of an impact it would probably have in real situations. And very clearly, you can never understand the real impact until you have used it in a real situation. But as has been said before, it's not our job to create some emergency incidents and test the system. So the best we can do is to develop models and simulate them. And it is well known that a lot of these models have been proven useful for such scenarios. And in the US, they have huge war rooms and decision theaters where we play these sort of games. And that's what we are trying to provide. So in summary, what we are trying to really to provide is as one part of the project, to provide people like you with an indication of what sort of technologies are out there that could be interesting. Provide tools and models for exploring the effects of different strategies and different technologies, and essentially provide policy recommendations. And if you look at the scenario I described with the evacuation of the building, you could very easily imagine that you could have, just like in the US, you now have a law that says that every mobile phone must be able to locate itself. You could very well imagine that you could make a directive that would say that every mobile phone has to have an emergency mode which can be activated from outside, that lets it be used as a relay station that can propagate information. And it is not something that would create any sort of significant costs to the mobile phone manufacturers. This is just, I don't know, a couple of hundred of lines of codes to be put on the mobile phone, maybe a couple of thousand of lines of codes. And those are the things that we hope to be able to produce. Yeah, and one last remark into the future. So the EU is now trying to put this program further. There's going to be sort of a flagship proposals where they try to fund huge projects in the range of hundreds of millions of euro. And one thing that we are trying to propose there is to develop a, we call it Living Earth Simulator, which is something that would be able to pull information from all those tweets worldwide, from huge number of phones and cameras, and try to create something like a real-life simulation room where you could simulate crises and view crises in real time. Okay, that's it.
Thank you very much. Are you going to go straight into Alois?
No, I would say let's have the question session and then go to the Alois talk. I think it's better.
So, sorry, just one clarification on the traffic. When you show the graph, the second graph.
The next talk we'll talk about the traffic part of it.
Okay, the second graph that you showed here.
Right. The second graph, you mean the
one with the pass, the optimum pass, or
the
one before?
Oh, this one you mean?
One.
Yeah. Okay.
Am I right to say that there is a kind of optimum around 40 people? If it goes beyond 40 people, it becomes useless also too?
No. If it's less than this. So essentially what happens if you have less than the number of people in the area, then people do not meet often enough to correct each other. And then it becomes useless.
Okay.
So it's actually the type of thing, the more people you have who communicate, the more useful the system becomes.
Okay.
And the interesting thing is that it's not like, the more people, the more useful. It's rather like, it stays useless, and then comes a point where it sort of rapidly transits into a useful system.
Okay, all right, thank you.
And useful means that, the error stabilizes here at 2 meters. So here it just grows indefinitely, and in a useful phase, it just stabilizes in a certain distance.
Thank you.
That's, of course, an average.
Yes. So I think we've got 2 phase transitions, yes?
Yeah.
Thank you. In terms of the test trial or the validations of this system, I don't know if you collected any data, because there is a real scenario in Haiti. I don't know how advanced is the infrastructure of the network, but this is a typical example which you could validate that, whether it's underground subway. Is there any comments or remarks on this? Thank you.
So, no, we didn't go to Haiti, but we actually have now work on validation. So, for example, so in this, the data that went into the error was extracted from experiments with students. But we will be running one experiment now in Malta. Malta Civil Protection Department is a partner in the project, where we will inject 20 students with mobile phones into a crowd in a concert, a crowd of a couple of hundred of people. And we are trying to look exactly at this, having these 20 people with phones, how can they communicate? How can they what can those phones tell us about what's happening in the crowd? We then will be running next experiments, that's sort of unofficial. We're talking to the Allianz Arena in Munich, which is the stadium of the Bayern München football team. And we would like to distribute applications to people there and have a couple of thousands of people involved in the project. So we're actively, definitely right, there's things that have to be grounded in real life experiments, although those are difficult because you're talking about a large number of people, but we are working there.
Thanks, Vol, for your interesting presentation. Just follow up on a previous question. I just want to extrapolate a little bit and ask you, you mentioned in your presentation that you based your directioning of people based on their mobile devices and so on. All that I think looks very feasible and credible in a normal situation. But when we're talking about the emergency situation in an underground, for example, or in a stadium or another shopping center or something like that, we know that the emergency services have a loudness of about 80 dB or over based on where you are. And in those circumstances, what assumptions have you taken into modeling? How do people behave? How is panic taken into account into that? And at the end, how will all these devices, or someone will take lead if you say, but is that something that you have taken into assumptions? How is that working?
So first of all, how people, you talked about, I don't know, the level of noise and how do you detect panic. So we don't know how to detect, we have never tried this, so that's one of the things we're trying. So the experiments where we try to, as I told you in Malta, detect certain crowd behavior. So in a concert you will not have panic, but you do have sort of emotional arousal, for example, of people. So we are trying to work on it. Now, for the next part of question, how do we see how things like leadership, those are things that we are trying to experiment with. So again, we would like to do a workshop and try to see, there's established procedure in sort of human-centered design that you present, you do experiments with people, see how they would react, and then based on this you can do simulations. We also have some models, and there are some mathematical models of sort of emergent leaderships and group formation and network formation and this sort of stuff. So people working on this.
For example, reading through the reports on 7/7, there were quite a lot of examples of emergent leadership. That doesn't mean that it lasts for a long period. It could be fairly ephemeral, that in a particular situation for half an hour or whatever, somebody actually emerged as a leader. And these are some of the things we're trying to understand. What actually facilitates emergent leadership. Okay, I've got one. Was there one there? No, I think one here and then there. No, here first.
This is excellent and fascinating work. The thing which is interesting me about this specifically is that in the developing world, there's a good chance that mesh networking will become the standard way of doing provision of services rather than sort of tower-based networking. So you might actually have much, much richer access to this kind of data in developing world countries in 5 or 10 years. Do you think that changes the dynamics very much, as it being a kind of backup function on the phone to being a normal foreground function? Do you have any thoughts on that?
I don't know. I mean, the idea of this mesh networking has been around in the scientific community for a very, very long time. It never took off. And I believe in developed countries it will never take off because there's no money to be made in this. So beyond teenagers sending some videos over the phone, it will not take off. And yes, you're right. There was this very famous MIT experiment where they actually equipped a bus with a wireless LAN access point. And because they did not have cables, the bus would just go around from village to village. And when you arrive in the village, it would simply collect the data, and the next day it would bring back the data. So if you wanted to see a web page, you essentially order it one day, it would be delivered the next day. But so it does change the ability, but I don't know if it would change the behavior, because virtually, if you look at the social networking, you now do have something like peer-to-peer connections, although it's being done over GSM. Yeah. So, you know, if you look at Twitter, then Twitter is actually nothing else than a peer-to-peer network that is just being implemented over another technology. Yeah. So I think the technology is transparent there. But I believe that the mesh networking would be something that with very, very small technical effort could be useful in emergency situations, because unlike in everyday situation where it actually subverts the business model of the providers, it is something that does provide a useful function. But it will not happen unless somebody orders it to happen.
Thanks. I'd just like to quickly add a couple of points to the previous question before last about panic and leadership. Panic, we found in lots of behavioural studies, is usually notable by its absence. That the classic view of what mass panic is, 50 years of studies by sociologists and experimental psychologists have found that it's usually not there. Clearly there's emotional arousal and fear, but that's very rarely manifested into behavioural actions of pushing, trampling, etc. Secondly, the point about leadership, I just agree completely with what you said and build on it, that the idea of leadership, leaders often emerge from crowds, but whether or not they're influential in the crowd depends on whether they represent the crowd. So in 7/7, you had heroic people like Paul Dadge, the off-duty firefighter who was helping people at Edgware Road. We would argue that those kind of leaders become influential because they represent a calm, resilient norm. We got some very interesting behavioural data from the Piccadilly line train that was bombed between King's Cross and Russell Square, in that we gathered information from survivors that two leaders emerged. One who was quite panicky, who said, we have to get out now, we have to get out. And another more calm leader who said, no, let's wait, the emergency services will know we're here. And the second leader was listened to more, and we would argue from a psychological point of view, because they represented the crowd better than the first leader.
I want to add here, because a lot of the material also that we looked at, and I will use the 7/7, where you have the phase transition from where there was panic, people were screaming when initially they were injured. Someone said, please be quiet, because we actually want to hear who is seriously injured. Since they couldn't see, there were no lights, they could only hear. And there was that calm. So we have the phase transition from, quotes, panic to calm. What we're interested in is in the reverse. Not just why does it go into panic, but why does it go into calm? Because that is the real key. And so others, colleagues who are working in that area, see me later, because I think there's some very interesting material there, particularly in this phase transition aspect.
So one comment on the leadership and electronic media. So one person in our project is looking at Twitter feeds and trying to evaluate them. And the interesting thing that he noticed is that if you look actually in the Twitter world, you have exactly the same situation of people emerging as leaders. So essentially, if you look at the number of things that have been retweeted, then you will find that in every discussion, you can identify 2 or 3 key people who are the ones leading the discussion, and the same you can find in Wikipedia and other online media. So it's quite interesting to see that it happens in the virtual world as well, and it would be interesting to see how these two worlds could essentially collide. So you would have this one person being the information leader, spreading the information or collecting it, and the other one possibly being the leader because of being, I don't know, strong and tough and whatever, and how that would play.
Are there any more points? Sorry, did you? Yes. I think right at the back there.
A lot of the modelling that you were talking about here is based on mobile phones. Do you see the logical extension into tablet PCs and TomTom traffic devices, those kind of... Is that where you can see the modelling going in terms of your sources of information as we carry around ever more complex devices about our person?
Well, the answer is that what I see is that in the long term, coming from a technology point of view, this distinction is going to blur. And actually you see that if you look at the iPad, then the iPad is an oversized iPhone. It's just a matter you people who use the iPad trade the inconvenience of having something large to carry for the convenience of having a screen on which you can actually read. So when I talk about mobile phones, I certainly, phones are not phones. today I don't buy a mobile phone to actually talk on it. I buy it as a computer. And a lot of people are doing that. So I think your comments go in the direction that I don't know if people will be walking around the subway with iPads, but those devices would converge. So you may have, for example, somebody who will actually take out his iPad because he can see the plan better. So what will happen, to bring it to the point, is that those devices will become more common, much more powerful, equipped with much more sensors, and this capability will grow. And the other thing that will happen is that the younger generation will become more and more dependent on those devices. So we already have this locate me, and people will just get used to being told by their phone what they should do.